Okay. Good morning, everyone.
It's good.
Good. Okay. Sorry. I'm playing with the Zoom setting. Okay, great. So I want to thank the organizing committee for giving me this chance to present this wonderful workshop, which has been really nice. And since I figure among all the today's speakers, I'm probably the last experienced observer, I figure I should talk last about the observation and talk more about the motivation, why we would be interested in the gas kinematics in the molecular clouds. In particular, I want to talk about what's the role played by the turbulence during the star forming process. So I would like to start with the beautiful image of this life cycle of the star. Even though when talking about star formation, we mostly just talk about the first half of it. So this is a simple picture of the process of star formation. It's way simplified, I know, but the basic idea is it's evolved from the interstellar cloud. In some overdense region, it can become the dense core. Then it collapse and rotate to form the disk and protostar system, and then it's form a star. So this simplified four-stage picture was first illustrated in this Shu Adams-Lizano star formation paper in 1987, which is the paper every star formation paper should cite. But after 20 years of this paper, there's an updated review by McKendall Stryker. And as the author stated that most of the progress on star formation theory in the last 20 years are based on the advanced knowledge of turbulence. And they also point out that together with the magnetic field and self-gravity, turbulence is one of the most important mechanisms controlling the star forming process. So what's turbulence in the molecular cloud? By definition, it's intriguing enough because it's pointing to some it's irregular state of motion, but you also expect turbulence to have some scale-dependent spatial correlation. So it's not totally random motion. And typically, we use the line width or the velocity dispersion to trace the amplitude of a turbulence in the cloud. And there's a long non-correlation between the velocity dispersion to the size of the cloud or the clump. I think the first way proposed by Larson. And there are theoretical explanations behind this parallel correlation, which I'm not going to talk about today. I just want to point out that this indicates that the turbulence is definitely a multi-scale phenomenon, which means when we interpret the velocity structure in the cloud, we have to be careful. Also, the turbulence in molecular clouds are compressible supersonic gas flows, which means it could be supporting the cloud from collapse. In the meantime, it could also initiate density enhancement. There, of course, should be magnetic field playing here, which makes things even more complicated. But that's not the main focus today, so just ignore that. So on the upper right, I have a beautiful image of torus in 12CO. It's just showing that the line of sight velocity within a cloud region could vary a lot. However, the other point I want to make is if we zoom into the filament region where the cores and stars form, we'll see that the line of sight velocity change systematically from one side of the filament to the other side. So this is a hint of the filament creation by compression of a turbulence. So let's go back to this four-stage star forming picture and ask, what does turbulence play during this process? So a roughly overview is, first, the large-scale turbulence collide with each other, compress gas to form some overdense regions. Then, because the velocity structure is not smooth and not uniform in the cloud, some regions will be more compressed than the other regions. So these overdense regions, overdense subregions, will become the seed of cores. And if this seed of core can get rid of the magnetic or thermal support, then it can become gravitationally unstable, and it will collapse to become the protostar with the disk. So all this, where I mark the red, text in red, are related to the gas dynamics. So we see that all these processes are somehow interconnected. So does that mean there could be some kind of connection or correlation all the way from the cloud scale turbulence to the core scale velocity structure and down to the disk rotating axis. To answer that question, or before answer that question, let's go back to look at what does the classical theory of star formation say. And actually, in the classical view of a star forming process, it is described as an isolated and quasi-static process that a dense core will preferably flatten along the magnetic field line, and because of the flattening and the conservation of angular momentum, it will start to rotate. That means the magnetic field direction, the minor axis of the core, and the disk and the rotating axis of the core should all be aligned. And in addition to that, if we assume the disk rotation and the core rotation is aligned, and since we know the protosphere outflow should be roughly aligned with the disk rotation axis, this means the magnetic field and the outflow should also be aligned. So in this simplified, idealized scenario, everything should be aligned. However, there's a long-known problem with this picture, which is the magnetic braking catastrophe. Sorry. This effect is that if everything is aligned so perfectly, then the magnetic field line will soon be twisted because of core rotation. And the tension from this twisted magnetic field line will try to straighten up and try to slow down the core. So as this movie shows, the rotation of a core will soon be slowed down, and the angular momentum will soon be removed by the magnetic field. And soon everything will just not rotating, and there will be no disk can form. So this is a huge problem because we know there are disks. So there have been many studies toward this issue, and most point to that there should be something missing in this classical picture, and most probably is the connection from the environment to the core. So from the observation side, there have been many studies to study the velocity structure connecting different scale. For example, in the CLASSI project, which maps the several regions in the Perseid molecular cloud. And from this map, it seems like the cloud scale velocity structure seems to go into the core structure, which is instead on the bottom right. Another example is by Ian Stephens, who looks at the correlation between the outflow direction traced by SMA and the filament orientation traced by Herschel. And he found that it seems like there is no correlation between these two structures, which means if the outflow is correlated with the core rotation, then the core rotation is not correlated with the filament orientation. The slightly different example is using the GBT ammonia survey data by Chen. He looked at the location of the dense cores and compared that to the velocity structure in the cloud. And he found that it seems like this core all locate at local maximum or local minimum of the velocity, line of sight velocity. So this may mean that these cores are formed or triggered to form by the compression of the gas flow. The other example is just something we done last year with two undergrad students, and Rachel Friesen and Laura Fiesel here. We compare the core orientation as traced by the GBT ammonia survey and to the cloud scale magnetic field as traced by Planck. And we found that the correlation between these two directions seems to vary from cloud to cloud. So this could say something about the turbulence level within each cloud. And different orientation could just mean in different cloud, the turbulence is playing a different role. So these are just some examples, but these are mostly just on the cloud scale. And what about the core scale? Well, it's not new to observe velocity inside the core, especially on the core rotation. Here I put the quotation mark for rotation, which I will explain later. So it has been proposed very early in Alisa Goodman that if the core is rotating like a rigid body, we should be able to observe a linear velocity gradient across the core, which can be used to derive the specific angular momentum of the core, which is defined as the angular momentum of the core divided by its mass. And as shown in this summary plot during this PP6 review in 2014, there seems to be some kind of correlation between this specific angular momentum to the size of the system, especially at the scale from cloud to core, which range over almost 2 orders of magnitude in size. There seems to be a parallel correlation, which seems pretty clear. However, when we look at the original data in some of these older observations, we realize that it doesn't seem like every core has a very obvious velocity gradient. But why? So go back to the assumption that the cores are rotating rigid body. We ask, are cores are really rotating? The main reason we want to mention this is even though we can always fit a linear velocity gradient to the observed core and derive a non-zero angular momentum, it still doesn't mean the core is rotating. In fact, in our simulations, most of the cores only have the rotational energy, roughly 10% of the total kinetic energy within the core, which means rotation is not the dominant motion in the core. The other reason we are interested in this is when we look at the correlation between the specific angular momentum to the size, we found that both the simulation and observation data seem to follow the same parallel as shown in the plot I showed in the previous slide in these papers. And however, we realized that this simple correlation is just consistent with the line width size relation of the cloud scale turbulence. So does this mean the core rotation is just a pure projection effect from the cloud scale turbulence? Or our cores are really rotating, but this angular momentum is originated from a much larger scale? Combined with our previous question, why not every core show the obvious velocity gradient? We ask, are all cores rotating? This means to answer that, we will need a survey study to get a good statistics. However, the more severe problem of this is, can we really believe that what we observe is real? So for example, it could be possible that for not enough resolution, we will miss either the linear velocity gradient, or we will interpret something more complicated as linear velocity gradient. So to properly study this problem, we need some kind of observation with both high resolution in both spatial scale and the spectral scale, because sometimes the velocity difference across the core could only be like 0.1 kilometer per second. We also need to cover a large enough field of view so that we won't miss any emission. So after yesterday's talk, I know all this specific sounds pretty familiar, because that's GBT with Argus. So here I show some spec that with Argus. For a typical dense gas tracer and torch plots, 1 to 0 line at 93 GHz, the resolution is 9 arcsecond, the coverage is larger than 2 arc per minute, and the channel width can be super fine. And just to compare the ELMA ACA band, the ELMA ACA band 3 for torch plots, similar angular resolution, much less recoverable scale, and a much worse channel width. And on the right, top right, I just show how the spatial resolution could affect the interpretation of the velocity field. So both are with GBT, one is ammonia, one with 30 arcsecond beam, and one is N2H plus with Argus with 9 arcsecond.
2-minute warning for you.
Okay.
Thank you.
For those of you who are interested, this is a sensitivity test we run with Jialu Li in Maryland. So on the left-hand side, I have a simulated integration time on the field view. And the interest region is marked in the 2 arc minute by 2 arc minute region. And our right-hand side is the actual data. So we reached about 70 mK in about 2.5 hours, which is not bad for a typical N2H plus line. So with those in mind, we conduct a pilot study with Argus to look at some of the cores in the Perseid molecular cloud to look at what the velocity structure really look like. So on the right-hand side, I show both the line of sight velocity map and the PV diagram. So you'll realize that even though the line of sight velocity map seem to be pretty smooth, in the PV diagram, it really doesn't look like that. And this is where the super fine channel with the GBT can provide counseling. However, if we just assume this velocity structure are linear gradient and just feed it and assume it's rigid body rotation and calculate angular momentum and plot it back to the correlation, we found that they actually fit in the picture pretty well. So this means we have to be really careful when interpreting this data of the core rotation. So with that in mind, we proposed and got accepted a new GBT large program to survey all of the dense cores in Perseus. This will include around 100 targets and will take more than 200 hours to complete, which will spend over 4 years. With completion of this project, we are hoping to answer some of the fundamental questions on the core rotation and core formation, especially on, for example, what's the what are the percentage of cores are really rotating, or what's the origin of a core's rotation. So to summarize, turbulence is important in the modern picture of star formation, and which can play an important role from cloud all the way down to core or even disk. And Argus, because of this multi-scale behavior of turbulence, Argus is the ideal instrument to map this, so follow this process. And I want to mention that we are also doing parallel theoretical study on how to properly model the velocity structure within the core. And we hope to follow up some of the cores using ALMA to map the innermost region of these targets. And we actually have some preliminary result of our cycle 7 ALMA project, which already shows some interesting structure of like the multi velocity component along the line of sight. So with that in the background, I thank you for listening.
Thank you very much. We do have a couple questions. We have a questions questioning why the spatial resolution of 0.01 parsecs is needed to assess core rotation. Do you need that higher resolution?
Right. So because the core, yeah. So I guess that go back to the question. How do we define a core? So when I say core, I'm saying the structure between 0.001 to 0.1, right? Yep. So it's not like the cloud core, like 2-3 parsec. So if a core is about like 0.1 parsec or even smaller, we need a higher resolution.
Okay, so the dense cores, not the big, like the bigger clumps. And then we have
not the clumps.
Yeah,
right.
We have another question about N2H+. Is this really the most suitable tracer to map turbulence in dense cores? This is usually converted to N2D+ in the inner region.
Okay, so I'll say I'm not a chemist and I'm not an observer, but I know N2H+ is a good tracer for cold dense gas. So it's a good tracer for velocity inside the core. I'm not saying N2H+ is doing a good job on the cloud scale, which I think CO would do a better job, which there's also another thing I think GBT-Argus can do. And I'm interested in that too. But yeah, I'm not saying N2H+ can trace the turbulence in the cloud scale. Sorry, if I say that, I'm sorry.
Okay. Yeah, and we can do, Argus can do the N2+ at 77 gigahertz for those interested. And then one final question. Is there interplay between the degree of turbulence and the intensity of the magnetic fields?
Yes, I think so. And personally, I believe the interplay between the turbulence and magnetic field is also scale dependent, just because the amplitude of the turbulence is scale dependent, and the magnetic field strength is not very that much compared to the turbulence. So I would think the turbulence is dominating over magnetic field at a larger scale, but at a smaller scale, the turbulence decaying and the magnetic field get stronger and stronger. The magnetic field will take over.
Okay.
I hope that answers your question. I'm not sure.
Well, if there's a follow-up question, the person who submitted it can put in another into the Q&A, and you'll be able to see the Q&A. And so feel free to answer, ask further questions if you want. We're going to move on to our next speaker.